Today we are going to add another very powerful tool into our tool chest of physics problem solving tools. And that tool is momentum. So pay close attention here. Momentum is simply mass times velocity. We use the letter P usually to represent momentum because momentum starts with the letter P. The P is silent. Actually, I'm kidding. There is no letter P in momentum, but for some reason, traditionally, we use P to represent momentum. Now, momentum is a vector, right? Mass times velocity. Velocity is a vector, so momentum's a vector. Sometimes we'll talk about the magnitude of momentum, and we'll say the magnitude of momentum is equal to mass times the magnitude of velocity. But in general, it's a vector. And momentum has units of kilograms meters per second. All right, mass times velocity. So now we can work a problem now that we know what momentum is. A tourist accidentally drops their iPhone over the edge of the Golden Gate Bridge. If the iPhone has a mass of 112 grams, what is its momentum after it has fallen 10 meters? Well, momentum is just mass times velocity. We know the mass. We just need to find the velocity after it's fallen 10 meters. Well, we can use energy to find that, right? Because work is just a change in kinetic energy. That's easy, but that's still too hard because we have an easier way because all of the forces involved are conservative. It's just gravity. Gravity is a conservative force. So instead, we can think in terms of conservation of energy. Energy final equals energy initial. If we define y to be 0 after the phone has fallen 10 meters, then after it's fallen, it only has kinetic energy. And then at top, when it's just falling, it has no kinetic energy, it just has potential energy. So the energy at the bottom is 1/2 mv squared, and the energy right when it's dropped is mg times the height that it's dropped. Okay, so we can multiply by 2, divide by m, take the square root, and now we have a formula for velocity, multiply that by mass, and we have momentum. But momentum is a vector, and all of this has just told us the magnitude of momentum, but we know that the phone is going downward, the velocity is in the downward direction, so momentum is just negative m square root of 2gh in the y hat, the j hat, which is the y direction. Now quickly let's check our units, make sure we did this right. The units of momentum are kilograms meters per second, and what we have are units of kilograms times the square root of meters per second times meters. That's meters squared per second squared. Take the square root. Everything works out. Okay, so then we plug numbers in, and we find that the momentum of the phone is negative 1.57 kilograms meters per second in the j hat direction. Yay! We found the momentum! But who cares? Why do we want to know how to find momentums? What is momentum even good for? Well, to understand that, let's think back about energy, specifically kinetic energy. We found that the change in kinetic energy is equal to the work, which is the integral of force with respect to distance. And this we derived from Newton's laws, or rather we showed that it was consistent with Newton's laws anyway. And, you can derive it, we just didn't. And it made a lot of problems much easier. So the hope is that momentum, which is sort of similar, right? The change of momentum is the integral of force with respect to time rather than distance. Well, wait a minute. I thought momentum was mv, so change of momentum would be m delta v. Well, let's run with this. So if I take the integral of force with respect to time, the integral of force is just, well, force is mass times acceleration. The mass is a constant. It comes out of the integral. Then you just have the integral of acceleration. And we know the integral of acceleration is velocity. So there's change in velocity. So that's mass times change in velocity. Change in momentum is mass times change in velocity, right? If momentum is mv, then delta momentum is m delta v. And we got that from our integral. So, okay, there we are. So just like changing kinetic energy is the integral of force with distance, change in momentum is the integral of force with time. So it's sort of similar. Maybe it can be similarly useful. So once again, it's derived from Newton's laws, and it makes certain problems much easier. Now, to see how it makes problems easier, let's think about Newton's third law. Imagine I have two objects and they interact with each other. The change of the momentum of object 1 due to this interaction is just the integral with respect to time of the force of object 2 on object 1. The change in momentum of object 2 is just the integral of force of object 1 on object 2. But Newton's third law says that the forces on these two objects are equal and opposite. If the force of 2 on 1 is equal to negative the force of 1 on 2, the force of 1 on 2 is equal to negative force 2 on 1. So we'll plug that in. So now our integral is just the integral of negative force of 2 on 1 dt. Well, that's just minus the change of the momentum of object 1. So the change of the momentum of object 2 is negative the change of momentum of object 1. So if I add them together, I get no change in momentum. Or in other words, well, okay, if I have a more complicated system with many particles, many objects, you can do the same sort of analysis and you find then that the change in the momentum of all of your objects added together, all of your objects that are interacting added together, it equals 0. Or in other words, the initial momentum of your system is equal to your final momentum of your system because the total momentum of the system doesn't change. So now we have a conservation law, just like we worked with energy, all right? And we can use that to solve problems. So just to rehash, momentum is mass times velocity, change of momentum is the integral of force with respect to time, and momentum is conserved. So here's a problem we can work with this. A 183-pound running back running upfield at 18.2 miles per hour collides with a 205-pound defensive back running downfield at 15.3 miles per hour. The defensive back grabs the running back and holds on tight, such that after the collision, they are both moving at the same speed. How fast are they moving right after the collision? Well, if we knew the force of one of the players as a function of time, we could divide that by mass to get acceleration, and then we could integrate that to get velocity. But even if we knew the force, that would be way harder than what we're about to do. So be grateful that we understand momentum because it can make our lives a lot easier. So let's ask here. First of all, is energy conserved? Yes, energy is conserved, but that's not really the question we want to ask because energy can go to all kinds of places. Heat, sound, crushing of rib cages and whatever. So the real question we should ask is kinetic energy conserved? And the answer is no. It's not conserved. And if it's not conserved, at least does it go into some potential that we can deal with? Are the forces involved conservative? No. Cracking ribs, muscles tearing, heat being generated, that's not, those aren't conservative forces. Is momentum conserved? Yes, momentum is always conserved. So even if kinetic energy is not conserved, even if the forces aren't conservative and we can't use energy stuff, momentum is always conserved. So let's use that. The final momentum must equal the initial momentum. Well, the final momentum is just the mass of the running back times the final velocity, right? They both have the same velocity in the end because they're stuck together. So it's the mass of the running back times the final velocity plus the mass of the defensive back times the final velocity. Well, the initial momentum is the mass of the running back times the running back's initial momentum plus the mass of the defensive back times the defensive back's initial velocity. So we've got an equation that tells us, that we got by using conservation of momentum. Well, notice on the left we can factor out the final velocity, and then if we just divide by mass running back plus mass defensive back, we have a solution. There is our solution. Plugging numbers in, we find that their final velocity is 0.500 miles per hour in the upfield direction. Wasn't that easy? Conservation of momentum is awesome. All right, now we need to tell you what impulse is. Impulse is defined to just be the change in momentum. So if I do something to an object and its momentum changes, that change in momentum is the impulse that I gave to that object. And of course, we remember that the change in momentum is just the integral of force with respect to time. So change in momentum is impulse, and that's just the integral of force with respect to time. Right? Remember when we did energy, we said change in kinetic energy is work, and work is the integral of force with distance. Well, with momentum, change in momentum is impulse, and impulse is the integral of force with time. Okay, so a baseball is pitched toward a batter. Right before the 140-gram baseball hits the bat, it is moving at 90 miles per hour, which is 40.23 meters per second. Right after being hit by the bat, it is traveling at 110 miles per hour, 49.17 meters per second, in the other direction. What impulse did the bat give the ball? Well, impulse is just change in momentum. And just to make our lives easier, we're going to drop the vectors, right? We know this is a one-dimensional problem. The ball comes in going one way, goes back out in the exact opposite direction. So we'll just do the scalar version of this. We'll just look at magnitudes. All right. Well, we're not doing magnitudes. This is still a vector, but in one dimension, right? We can use minus signs to represent the other direction, so we can kind of treat it like it's not a vector. All right, well, the change of momentum is P final minus P initial, which is mass V final minus mass V initial. Factor out the mass. The impulse is just mass times V final minus V initial. And the mass of the ball is 0.145 kilograms. The final velocity is 0.4917 meters per second. I made that positive, so I'm implicitly saying the final direction of the ball is what we call the positive direction. The initial velocity then is in the other direction, in the negative direction, so it's a negative 40.23 meters per second. Plug it all in, and the impulse that we give the ball is 13 kilograms meters per second. So just to summarize and compare, got one more thing. Momentum and Newton's second law. It turns out the momentum is very closely related to Newton's second law, right? Newton's second law is force equals mass times acceleration. But acceleration is just the derivative of velocity with respect to time. So force is mass times the derivative of velocity with time. But mass is a constant. It can move out of a derivative. It can move back in again. So force is equal to the derivative of mass times velocity with respect to time. But mass times velocity is momentum. So you can also think of Newton's second law, in addition to saying, force equals mass times acceleration, it's equivalent to say that force is equal to the time derivative of momentum. Okay, so just a quick summary of what we talked about today. We talked about momentum, and we can compare it to kinetic energy. Momentum is a vector, kinetic energy is a scalar. Momentum is equal to mass times velocity. Kinetic energy is 1/2 mass times velocity squared. Change in momentum when something happens to an object, we call that the impulse. The change in kinetic energy of an object, we call that the work done on the object. And of course, the impulse is the derivative of force with respect to time, whereas work is the integral of force with respect to distance. So there's some nice parallels here, some nice analogies. They are both closely related to the second law. They're both derived from the second law. Momentum is always conserved. Total energy is conserved, but there's lots of different forms of energy, so kinetic energy is not always conserved. We have a special name for the units of energy. Energy is kilograms meters per second, meters squared per second squared, and we call those joules. There's no special name that I'm aware of for momentum. It's just kilograms meters per second. Sad. Anyway, that's the end of our discussion on momentum.